morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation, and we are moving forward with our module 4, which is Distribution Network Optimal Power Flow Analysis. We started the discussion on the centralized and the distributed OPF algorithms different in the last class, and we will continue that today as well. So, last class we have seen the vanilla ADMM and the accelerated ADMM version of the distributed OPF problem solution methods, and today we will see another promising method which is very fast compared to your ADMM, and that is called equivalent network approximation method. So, that is explicitly derived, that NAP algorithm, we abbreviate the equivalent network approximation as NAP, and that is explicitly developed for radial distribution system only, and that makes the algorithm very fast. You will see in later slides with DERs. Then the local optimization problem is same as like what we have seen for the ADMM. Then the NAP algorithm actually leverages the radial structure of the distribution network topology. That means there is only one child area and one parent area for a particular area. So, each area is managed by a local agent responsible for solving its specific local OPF problem while coordinating with neighboring areas. Okay. It works on the principle of network equivalence method, and what with this method what we do, based on this principle, only the shared buses between the areas are modeled as voltage source for downstream regions and load buses for upstream regions. That means, let us say you have three areas, area 1, area 2 and area 3. So, for area 1, area 2 is the child area. So, it is only intended to know how much power it has to give to area 2. So, that information will only go from area 2 to area 1. That means, area 2 will act as a load for the area 1. Similarly, for area 2, area 1 is an infinite voltage source from where it can take the power like a substation. So, only the voltage data will be sent to area 2, which says for every child and the parent area, child area only serves the parent area with their load data, and parent area only shares the voltage data with their child area. So, with this consideration, the NAP algorithm works. So, in ADMM what I have seen, that both the areas will share both voltage and the power values, but in NAP this communication burden, that which data you will share, that has been reduced, and only few data, one of the two data are shared with your neighbors depending upon where it is situated. So, each local agent using known voltage data from the upstream and power flow data from the downstream simultaneously solves its OPF problem. Okay. Then they exchange the updated boundary variables with their adjacent agents. Specifically, the downstream agent communicates the power flow information on the boundary buses to the upstream agent, while the upstream agent shared the bus voltage details with the downstream agent. Okay. What we have seen here. So, for area 2, the downstream area is area 3. So, that will act as a load and it will take on the power data from it, and area 1 will act as a parent, and that is the infinite voltage source. So, it will get only voltage data from its parent area 1. So, this iterative process will continue till the consensus is achieved. So, consensus is must for any distributed OPF, whether it is ADMM or NAP, but consensus must be achieved between the areas as far as the sharing boundary variable is concerned. Okay. Now, what is network equivalence method? Network equivalence method says, let us say this is a distribution network and you separate this into two areas, this is area 1 and this is your area 2. If you have two areas and in between if you have a node, let us say node 8. So, for a given set of network parameters, the voltage profile and the branch power flows are unique, that we know from the load flow studies. For a particular generation, particular network, if you solve the load flow, you will always get the same voltage and the power flow values. You never get deviated values or different values. If you are getting, that means you did something wrong. However, if that is an unique, so that unique value you can share. That means you don't have multiple solutions, you have only one solution. So, you can represent for this bus number 8 the upstream area 1 or the for represented as a voltage source which is the bus 6. So, for this node 8, bus 6 has become a infinite voltage source V6. Okay. So, for that instant the voltage at node 6 is obtained from the solving the radial power network is unique. Similarly, the power flow between branches 8 and 9, that is also unique. Okay. So, therefore, the V6 or the voltage of the bus 6 and the complex power flowing between node 8 and 9 can be effectively used to approximate the network condition for the upstream and the downstream region. That means, for node 8, the upstream area is entirely approximated with the voltage of the bus 6, and the downstream area, that means area 2, has been entirely approximated by with the load or load flow, power flow flowing from the bus 8 to 9, and that we have modeled it as a load. So, you can see this entire network has been lumped together into node point for a particular node 8. So, that is the network equivalence, and this thing has been used for the NAP algorithm to get the faster convergence. So, if you see the NAP algorithm schematic, you can see that for the upstream area, you will get the downstream area load values for a particular iteration. You will solve the optimization values and you will get the optimal voltage for the dummy bus. Similarly, at the downstream area, you will get the voltage values from the upstream area. You will solve that optimization and you will get the branch flow values for the dummy bus. Then share that for in the next iteration. Like for the next iteration, you will share the downstream area will share the power and upstream will share the voltage, and that will continue till you reach the consensus, and each this iteration is called the macro iteration. Okay. So, what are this NAP algorithm? NAP algorithm, if you see, first you initialize the boundary global variables like the same we did for the ADMM as well, 1 per unit for voltage and 0 per unit for the power flows. Set the residual threshold for the network or for the algorithm. So, here you have to calculate only one residual, not the primal and the dual, because you have seen that here we are not forming any Lagrange equation for NAP algorithm. Then start your iteration with I equals to 0, then increase your iteration by I equals to I plus 1, then solve your local OPF, that is normal OPF you will solve, not the Lagrange equation. You will solve the normal OPF and get your local solution. Then update your boundary variables by sharing the data with your neighbors, accordingly your parent and the child area. Then you evaluate the residual, because you are getting only one data from your neighbors. So, check that residual, and if that residual is lesser than your threshold, then you have reached to a consensus. If it is not, then do the iteration again. Okay. So, this is the NAP algorithm. So, we will see few case studies on these algorithms ADMM and the NAP, that how they perform. So, we will take the loss minimization of OPF problem as our basis. So, what is the problem? The problem is to control the inverter reactive power output from the DERs to minimize the total loss of the network, and we took the QOLP formulation, quadratic objective linear programming. Or so you have, this is your objective functions what we derived from this equation by putting the Vm phi close to equals to 1, okay, and you have linear model of the BFM of the 3-phase system. So, with this, if we decompose that into multiple areas, for each and every area we will get this problem. So, this power balance and every equations will get for that area, and this objective function will be revised accordingly for every area. So, previously the total objective function was summation of n. That means your summation is done for the entire network with n number of buses. That means all the buses present in the network. But now the objective function has been reduced only for those number of buses present in that area. Okay. So, that is why we replaced the n with the nh, and that will do in parallel for all the areas we have taken in that network. So, this is the IEEE 123 bus system. We will test that one, and the simulation is conducted under base load condition, what is there in the IEEE. We just modified that with the 10 DERs or the inverter based resources, that is the PV inverter. Okay. We have 50 kilowatt rating and 60 kVA of the inverter rating. We segregated the entire network into 4 areas, area 1, area 2 and area 3, area 4, and their substation voltage is limited to 1.05 per unit, and the voltage values are allowed to vary between 0.95 per unit to 1.05 per unit. So, with under this consideration, we will see how we can solve it. So, we have solved this in an i7 processor computer with 32 GB RAM. The key performance metrics recorded include network power losses, solution convergence time, and the number of macro iterations completed for each and every distributed OPF algorithm. The IEEE 123 bus system is having 123 buses, 267 single phase node and 253 single phase lines. So, we will test for both centralized OPF and distributed OPF approaches to optimize the 30 independent decision variables, that is the reactive power output from the 10 3-phase DERs. Okay. So, this is the solutions. You see that this is the ultimate COPF solution. We will take the COPF solution as the base, because that is the ultimate, we have seen that that will give you the ultimate optimality level. Okay. So, if you take the COPF, you see that the total loss is coming out to be 47.06 kilowatt and the solution time is 51 second. Now, if you use vanilla ADMM, then you can see the convergence curve that it is taking almost 71 macro iterations to complete, and it has reached to 47.158 kilowatt solution. So, that is somehow comparable, that is nearer, but the solution time has been increased by almost 4 times. And you have to complete almost 71 iteration to get the solution, and you can see more fluctuations is there when it is converging. That means, it was a smooth convergence. Sometimes it is converged to here and then again jump to the another solution, bad solution, then again jump to another solution, then again coming back. So, more fluctuations we can see if we use the vanilla ADMM. So, now we use the accelerated ADMM without the adaptive penalty parameter, that means only with the predictor corrector method. We can see that the number of macro iterations has been reduced significantly. We have reduced from 71 to 27, and similarly your solution time has reduced from 193 to 76. Okay. Second, so you can see, and also the fluctuations in the convergence curve has been reduced to a very few, only 1 or 2 fluctuations we can see. If we add the adaptive penalty terms, then this will be further enhanced the performance, and you will get the solution with only 12 macro iterations, and the solution time is only 54 seconds, and it is mostly a very smooth convergence. You do not have any fluctuations. Why? Because your update of your penalty parameters is so smooth or so adjusted that it can take a very small step whenever it will reach to the close to the global solution. Now, you can see that NAP algorithm, which is designated for the radial distribution network, that is giving you close to the optimal solution with only 4 macroseconds, and that is also your solution time is also reduced to 8 seconds only. So, you are solving 123 bus system and each and every area in parallel. So, your total solution time is only 8 seconds. So, it is almost a real time solution you are getting, and also the convergence is very smooth, Another advantage of this NAP algorithm is that you need not to specify any row or any kind of parameters. You do not need that. So, you need not to set any penalty parameters for it. You need not to worry which value you have to impose for this penalty parameter to get the good convergence. It is inherently the network equivalence that will give you this convergence value. So, if you see the voltage plot for the phase A, B and C, almost the C and D OPF, the solutions are close or nearer. That means, whatever solution we are getting from the DOPF solution or the distributed OPF solution, they are close to the centralized OPF solution. So, we can say that the distributed OPF is a very good replacement for the centralized OPF. We have further extended the case study with different kinds of PV inverter models that we have studied in module 2. We have studied the volt watt model, volt var control model, fixed inverter model or grid following model. So, if we impose those models in the PV inverters or those control strategies with the PV inverters, how this distributed OPF will perform or even the centralized OPF will perform. So, for that we have changed a little bit with the 123 bus system, 4 areas segregated. All the loads have the DERs or the load nodes have the DERs. So, you can see the green nodes, they generally have the loads and all the loads have the DERs. That means there is almost 100% DER penetration. So, with this the load model and the PV inverter modes has been changed. First we will see with the load. If we have only constant power load of 100% and your all the PV inverters are running in the grid following mode, then it is taking almost 157 seconds to solve for the centralized OPF, and it is completing 83 iterations in 234 seconds, that is almost 4-minute time to get the convergence for vanilla ADMM. If you enhance the load percentage of the ZIP, if you see for both the distributed and the centralized, you can see the solution time is increasing for both the vanilla ADMM and the centralized OPF. Even the iteration number is also increasing, though keeping the inverter module same. But if you see with the more ZIP loads, your losses are becoming lesser. Why? Because you are imposing more and more voltage dependent loads. So, that means you are implementing the CVR strategy, that is a conservation of voltage reduction, conservation voltage reduction technique, which says if you make your loads voltage dependent and if you reduce the voltage a little bit, you can significantly reduce the power consumption. So, that is why if your power consumption is less, then your network loss will be also lesser. Okay. With this, if you see that with enhancement of the ZIP model, your losses are less, but your solution time is becoming more, because you are imposing more and more constraints with the optimization problem. So, if we further experiment this with different PV inverter controlling strategy, with the grid following mode, we have come to now volt var control mode. Now, we add volt watt control mode and then we add the voltage control, fixed voltage control mode. So, if we make 50% contribution with the ZIP load model and then we make the 50% of the PV inverters running at volt var control, then what you can see, your first you are converging within 83 iterations, but now you are taking more than 300 or 350 iterations to converge. And also the fluctuation within convergence is very high, because all the time you have to check the voltage. If the voltage is not proper, then your reactive power will get updated. So, each and every area it is cannot fix it output voltage or output power, because depending upon your power, your reactive power is changing depending upon your voltage status. So, now you say that it is 0.9, so you got some reactive power value, but at the same next iteration you got some 0.91 per unit of voltage. So, that will change your reactive power output, because it's you can remember that this is the QV droop characteristics. So, each and every variation in the voltage, until unless you are at the rated value, you will get an updated Q value. So, that will enhance the number of variables in your ADMM algorithm, and that will make the convergence process very slow. Again, if you add the volt-watt control model, then now not only with the reactive power, also with the active power, you are adding this droop characteristics. So, even your active power is also changing for slight change in the voltage of the upper area voltage. So, that will further lengthen your convergence process, and you can see more and more fluctuations in the convergence. This is worse than, and even you will get fluctuation at the convergence time if you add voltage control mode. Why? Because in the voltage control mode, what I have seen, to maintain that voltage, it is dispatching its P and Q. So, if every time your voltage values get changed, that means you have to track that voltage at each and every time. You do not have flexibility, you have to stick with that voltage. So, that will impose an extra constraint with the PV inverter operation to run at a specific voltage value, and that will give you more fluctuations when you share that value. You cannot agree. You shared some value with your neighbors, you got some result, and after some time you see that your voltage of your neighboring areas has changed. If that is changed, that means now you have to also update your solution. So, that is why you will see more and more fluctuation and longer solution time. If we summarize this in a table, we will see that the solution time has enhanced like anything. Previously, with this load, you can see it is only 7 minutes, 7 or 8 minutes. But with the increasing penetration of different controlling modes of the PV inverter, almost your solution time has reached to 1 hour for a single time step analysis. Same for vanilla ADMM also, this is around 55 minutes. This is somehow lesser to the COPF, but they are very close. And the number of iterations with the voltage control mode has increased to 2167. So, this is a very huge number. So, that is the effect of the PV inverter models and the loads if you use the distributed OPF. That means your distributed OPF, convergence of your distributed OPF is highly dependent upon which kind of load you have in your network and your DERs are operating in which mode. If they are operating in grid following mode, that is the most easiest mode of operation, then your solution time will be very less. But if your PV inverters are operating in different modes and your loads are also voltage dependent, that means now your parameters are also not fixed. Your parameters are also updating with the values of your neighbor or boundary global variables. If that is the case, at that time your convergence will suffer like a lot, and you will get a very bad convergence for your distributed OPF. So, at that time it is better to go with the centralized OPF if the size of the network is medium, small or medium. But if it is a large system, then you have to go with the distributed OPF, though you need larger iteration to converge. You like it or not, but you have to adopt it. So, we will see few commercial OPF solvers normally generally used for solving this kind of problems. Generally, we code the OPF in MATLAB, Python, GAMES or Julia, and MATLAB has very good library for solving these OPF algorithms. You can use linprog, intlinprog, quadprog, conprog and fmincon solvers to solve the linear programming, mixed integer linear programming, quadratic programming, convex programming or nonlinear programming. The fmincon is very good for solving non-convex as well, but it cannot take any mixed integer constraint. Other than that, you can add extra library as an external model with the MATLAB, that is the ELMIP. You can add the Gurobi solvers as well, Simplex solvers as well, integrated with the MATLAB. For games, Python also you have SciPy library, Pulp library, Pyomo library, GurobiPy library for adding with the Python to solve your basic optimization, linear programming and convex optimization. Same, you will get libraries for your games GAMS you can integrate with any outside solvers like Baron, CBC, IBM solver, Minus, Mosaic, Conocopt. You can just add, you can integrate with your GAMS and you can solve your OPF problem. It's a high level coding platform and specifically designed just to solve the mathematical problems. Then Julia coding language is now evolving and people are using its library, and it's a very fast acting solution process. Fast acting coding means for the same algorithm, if MATLAB is taking 10 minutes, Julia can take only 1 minute time or 30 seconds time to solve. So their libraries are very fast, but the implementation is little bit difficult and still it is evolving. So you will not get solution for all kinds of optimization problem in this Julia package, but still they have this GNU linear programming kit. They have convex over and under envelopes for the nonlinear estimation, and also few others solvers to solve your convex and non-convex optimization problem. So with this, I will end today's lecture and will continue with this OPF analysis in the next class as well. Thank you.